Yes.
Yes.
Okay.
Yes.
Yeah, I hope you can hear and see me properly. So good morning, everyone, to today's session. It's our second session, and this is where we start exactly. We go into detail about key things in sets today. So it's a very important lecture. It's the foundation. It may sound very basic to some of you, but later on, as we progress in the module, you're going to see how these notations, the things that you're going to learn in today's session, is going to be important in the future chapters that are coming. So it may sound very basic for some of you. It may sound a little bit complex for some of you, but at the end of today's session, please make sure that you've understood the main concepts and you are able to use these concepts henceforth. There will be a number, I'm pretty sure you've seen a homework already in on Google Classroom, so that would be due for correction in next tutorial, which is going to be on Wednesday. So make sure you're present in the tutorial. And then we're going to work out a few questions if time permits us today itself. But in the tutorial, there will be many more questions that we're going to sort out. Okay, so let's proceed. Just give me a second, please. Sorry about that. So just clearing out the disturbances. Yep, that's better now. So let's proceed. So what we're going to do, let me just share my screen. Hope you can see my screen. Nope, that's the wrong one being shared. Yes, we can.
The questions that you uploaded on Google Classroom is not there. It's just only the title.
Okay, I'll sort it out in a few minutes. Don't worry.
Okay.
That's who's speaking? Farhan, right?
Yes.
Okay, I'll sort it out in during the break. Thanks for sharing.
Yes.
Can you see my PowerPoint?
Yes.
Yes. Okay.
Yes.
Yes.
Okay, good. It's just that I'm not seeing exactly what you are seeing, guys. So for some reason, I don't know what's going on. Yeah. Let's proceed. Right. That's better. Okay, we're talking about sets. Sets are interesting since it is a very, very important element. Please, if you have any questions, since it will be difficult for me to jump from the slides to the comments out there. So I'd urge you just, if you have any clarifications, anything that is a little bit unclear to you, feel free to stop me and ask questions. That will be helpful for you. That will be helpful for me. It's going to be win-win on both sides. Okay, so please do clarify things as far as possible. So I'll try to make it as simple as possible in this for you. Okay, so set is a very interesting concept. In fact, not just a concept, but it is something that is, let me just turn off the camera because it's just gonna be too much. I'm at the university right now. So if you don't mind, provided you have the slides in front of you, whenever we have discussion sessions, I'll turn on the camera. Sets are very important as a software engineer. Set is a very important element. Why? Because whenever you look at a problem, right, in simple term, whenever you have whatever software that you will be that can you see my screen?
Yes.
Yes.
Yes. Can you see me writing?
Yes.
Okay.
Yes.
Whatever software that you will be using, just give me a second. Yeah. Whatever software, for some reason, I don't know what's going on. Oh, okay, I can figure out now. Yep. So let me just use the red pen. Oh, shit. Why is it not writing? Yeah, that's better now. Okay, so whenever you have a problem, right, the software meant, the reason why we have software is meant to solve a problem. I hope you get this. I hope by now, as a as a student, as a future software engineer, you understand the concept that software are meant to solve problems. I'll put an S to that, something that is very important to understand. As I said, please try to avoid, if you have any issues, so I think you swipe forward. If you can turn on your mic, because it takes me time to go back to your chat to understand what is happening. I'm just having an issue with my graphic tablet. That's why you had the slides moving that fast. So it's back to normal. Okay, right. So whenever you're talking about softwares are meant to solve problems. Okay, there you go again. Yeah, are meant to solve problems, and problems. I don't know what's happening to my computer today, but it sounds a little bit odd, but let's fit. Yeah, so problems are something that would be that are complex. So whenever you're talking about problems, they are meant to be complex. That's why you need a computer, a computational power, processing power to resolve a problem. Okay, so now to make so even though computers can solve many complex problems, right? They are able to solve many complex problems, yet we are still in a situation where computers have a lot of limitations. If it were to be able to solve so many complex problems, you would see robots, things around, a lot of AI, everything would have been fully automated. COVID-19 wouldn't have been an issue because computer could figure out what's the problem and a solution, and everything would have been so easy for us. But it's not the case. I hope you can see that around you. The technology seems to be to have turned out to be something very interesting, very important. Yet you can see that there are limitations. Computers are still at the level where it needs an input, it will process and give you an output, but it does not have the intelligent behavior. It does not have the intelligent behavior. There you go. That slide keeps on doing that. Let me just, to avoid this situation, let me just try to, just give me a second, guys. I just want to solve this issue. Let me just do it over again. I think it's just pointless to do it like this. Just give me a second. Just give me a second, please. I'm having issues with the graphic tablet. It's not working as intended. So every time I have to, it's moving slides instead of writing down things. So bear with me on this one. My apologies. So let me just remove this. That will be much easier. Okay. Should be good now. Okay, good to go. Can you see my slide?
Yes.
I hope it's good now. Okay, we're not going to have issues. So yes, so I was talking about problems, and we're talking about very complex problems. And when you look at the real world, the problem with computers is that they lack intelligence. I don't know if you agree with that. You do have intelligent computers around, but there are very few instances of these computers. We think they are very intelligent, but they are not. They still can't. They are not very rational in their. The word is rational. They are not very rational in their approach. What does that mean? They cannot take the right decision for us. They cannot do the right thing for us. So that's problematic. So one thing that to overcome this situation, mathematics, especially something called sets, can turn out to be very helpful, right? Not only sets, but other techniques that can be used. You will see that you will be very shocked to see that a lot of people who are working in AI, right, these days, those professionals, those people who are earning big money in AI are actually not computer scientists, but mathematicians, right? You'll be very shocked about that. Companies that are recruiting people to work in AI are mathematicians and engineers. I'm not talking about software engineers, but it could be civil engineers, it could be mechanical engineers. Why? Because they know how to solve problems using mathematics. Okay, so the topic today is all about sets. Why sets allows you to break down something which is extremely complex into different components, right? So one of the advantage of breaking down things is that it's more manageable, right? In terms of management, it's much easier. So you've taken something that is that big and you've taken small little chunks, you've divided it into small little chunks that are more manageable. So it makes it much better. So you can see right away from this drawing. So we had a set, then we have subsets in there. And these subsets maybe could have things that are common. So there will be some kind of an intersection between them and so on and so forth. So you can see the link between very complex problems in general, not only very complex problems in general, and sets. Later on, we're going to use sets to define functions. So functions, which is a very important element there. We are going to use sets, as I said last week, to define relations, which again is another very important element. So there are so many aspects that can be extremely useful later on to resolve problem. Tomorrow, I'll be having a lecture with AI students. And again, we bring back the concept of sets. If you could make your problem simpler by using sets, that is grouping them into subsets, by grouping them into sets, by grouping them into elements, right, that you can manage, it makes things a lot easier. So what is the definition? A set is a collection of objects, unordered in most cases, a collection of objects. These objects are sometimes called elements or members of the set. I want you to understand something which is extremely important here. We are doing something called applied mathematics. Even though we're taking all sorts of examples in sets in this module, you need to understand that it should be applied. You just need to see what kind of problem can be resolved using the concepts that you're learning. So it's not something bookish. It's not something that you're learning just for the sake of getting through the exam. It's a lot more than that. Okay, so I'm pretty sure you've seen that. I'm sure you've started programming. Some of you are already familiar with programming. You may have a variable in your code where you define a set of, let's say, variable letters, where you tell the computer, these are the letters of the alphabet. Okay. What you're doing, you're simply having a set called L that has letters of the alphabet in there. So if simply put, a software engineer can define those sets, right, and later on translate it to the programmers as these are the sets that are needed. So definitely you need to have variable that will host, that will contain those elements in the sets, it's much easier for them to understand. It's much easier later on to solve it. So there is a little example here, vowels in English alphabet. For example, the set V has those vowels of the English alphabet. The first 7 prime numbers, X. So these are those numbers. So it's very simple. It may seem very casual, very simple, but understanding the concept can be such an important element. So representing sets, and this is the most important element. How do you represent sets? If you want to solve a problem, you should be able to if you want to develop a system that can solve a problem, you should be able to represent the environment, the problem using sets. So representing a set by listing, right, enumerating the members of the set. Definition by property using a set builder notation. This is extremely important. This notation, this famous notation, is so important. Okay, I want you to understand how important these notations. I want you to take stock of how important these notations will be in the future as you progress in the chapters. So let's say here you have an example, even integers between 50 and 60. So you have a set. Before I say, we'll show you how to read those notations, how to understand those notations. Sometimes you're going to have questions where you have a particular, so a paragraph will be given to you. So you have a set of problems being explained here. Problems could be in the form of a game. Problems could be in the form of a problem in terms of IT. Problems could be anything that you can think of that could be a problem. And then you'll be asked to formulate, using set builder notation, formulate this problem using sets, right? So you have to formulate the problem using these methods, okay? Even integers between 50 and 60. One note before we go to the example, what is a set builder notation? Notation has 3 parts, a variable, number 1, a column, number 2, or vertical bar. So you may have this or this. It's a straight line, okay? Vertical, it's a straight vertical line, okay? As separator, and a logical predicate. Okay, we're going to explain logical predicate in another chapter, which is very important. So this is what is known as the logical predicate, right? And the bar that you can see here is the separator, and that separator is known as, which simply says that such that, and you have a variable here. Okay, so very important to understand this element. We're going to talk a lot about this in the coming chapters. So a little example, even integers between 50 and 60. So E is a set of, so one way of putting it would be enumerating those elements, and another way would be to use a set builder, X being such that it is an element of such that X is less than or equal to 50, and X is greater than or equal to 50, and X is less than 63, and X being is an even integer. Okay, so this predicate is something very important. It describes a lot of things. If enumeration of the members is hard, we often use ellipses. Okay, so ellipses would be ... Okay, but you have to be very careful, especially in software engineering, and especially in this module. You have to be extremely careful when enumerating using ellipses. When it's a set of integers, we can easily enumerate using those dots, because we know between those dots, it's very easy to know what are the numbers in there. But whenever you have a set of real numbers, sometimes it can be very tricky if you say 1, virgule ... to 10, for example. Okay, this could be extremely tricky if you do that. Okay, so you need to be very, very careful whenever you're using those ellipses. So set notations. So let's have a look at those notations. So far, so good, guys. Any questions?
So
Yes.
Can you
Yes, please.
can you explain again the ellipses?
Okay. The ellipses is simply the if you have, let's say you have a set that contains elements from 1 to 100. So you can use set builder notation, right? Like this one, like you're going to say x such that x is between 1 less or equal to x less or equal to 100, for example, or less than 101, and x is an let's say an integer, for example, and so on and so forth. Okay, so that's one way of putting it. That's builder notation. Okay, set builder notation. So instead of writing everything down, another way of doing it, x. So the set of numbers, let's call it s, for example. So s is this. So s could be 1, 2, 3, 4, and I keep on writing till 100. Okay, so that's another way of putting it. But you see that writing up to 100 can be very lengthy, tedious, and so on and so forth. So you can use ellipses to do that. Dot, dot, dot till 100. Now, the problem with dot is that since we are dealing with a set with numbers that are integers, right? We have no problem in putting dot, 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 because those dot, 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 those ellipses stands for 4, 5, 6, 7, 8, 9, 10. We understand it. But sometimes if the set is a real number, a set of real numbers, here you go again. A set of real numbers, it can be very tricky, right? It can be very tricky to understand what those dot, dot, dot stands for, right? So it could be integers is very easy. It's very discrete, but integers, real numbers can be very tricky to know what are those dot, dot, dot. So you have to be very careful. What the main takeaway from this is that you have to be very careful whenever you're using ellipses. If it's understood, it's very discrete, right? Those elements in the set are very discrete. So for example, you know, every element would be n plus 1 or n plus 2, n plus something, right? It's very distinctive, right? Then it makes sense to use dot, dot, dot. But if it's not the case, and numbers will vary, the elements will vary may vary significantly. So you need to be careful when using the dot, dot, dot. Is that okay, my friend? Whoever's asked the question?
Yes, thank you.
Okay, please, when you ask the question, since I'm not, I cannot see who is speaking, can you just kindly just tell me who you are, and then you ask your question. Thank you. So set notations. What are we on about? Let's have a look at those notations. S is equal to ABC refers to the set whose elements are A, B, and C. Pretty simple. A is an element of S, very simple. D is not an element of S, so that means A is found in the set S. D is not found in the set S. X is so how do we read this? So X is the set of all those X's, right? Such that P of X is true, right? So an example, if we have a set of integers, this will represent the P of X here. This is true. X would be between 0 and 10, okay? So whatever you're going to have as predicate here, it is true, okay? So this is known as the predicate. The green box that I've highlighted here is the predicate. So note something very important. In most cases, this could be regarded as the same set because they have the same element, but in this case, the element is repeated. right? But it could all represent the same set. It could all represent the same set. The sets can themselves be elements of other sets. So you can see that. Look at this a bracket inside of the bracket. So you have a subset in the set, right? So Mary and John, Tim and Anne being a set in the set in a bigger set. Okay, so the second list of notations, the second element of notation, the previous one were basic notations. So I'm pretty sure you know all of them. So a collection of elements. This is union, right? So you have a little example here. So union would be, so assuming D would be 5 and D could be, let's say, for example, not 5, 3, 4, and 5. And for example, C could be this, right? So the union would be of C and D would be 1, 2, 3, 4, 5. The intersection would be 3, 4. So subset is A has some elements of B, so A has some element of B. For example, unfortunately, we don't have, so here would be C would have some elements of D, for example. So you'll see that 3, 4, 5 is a subset of D. This is the more tricky one. What is a proper subset and what is a superset? A proper subset, A has some elements of D, not all. If it has all the elements, it's a subset. A subset. If it has some of the element, you see that 4 is missing there. This is known as a proper subset. Okay, so it's a proper subset. Okay, and then not a subset. Not a subset. A is not a subset of B. So 1 and 6 is not a subset of C, for example, to give you an example to put into perspective. Now, this is another tricky one. What is a superset? A has same element as B or more. So you can see that A has, so here, C has same element as D or more, for example. Here we're taking a different example. So the same, don't take the example for C and D. So if you have two sets, they have the same element. So exact same element. So this is known as a superset. And what is a proper superset? A has B's element or more. A has B's element, but it has more, right? So if it has equally, if it had 1, 2, 3, and 1, just like B, then it would have been a superset. If it has more element, A has more element than B, then it is a proper superset. If it does not have, A is not a superset of B. So if you have 1, 2, 6, even though you have 1 in there, but the rest is not present in the other one, is not present. So it is not a superset. Is that clear for everyone?
Yes.
Okay. We're going to have a few. Yes. Who's speaking?
Muntasir Hasan. For proper superset and
Oui.
superset. Can you explain it again?
Okay. For a superset, A has elements of B. So if A is equal to 1, 2, 3, and B is equal to 1, 2, 3, right, or 4, right? Let's keep it simple. A has same element as B or more. Forget about or more. If it has the same element, right, of B, right, then it is known as a superset. Okay, if it has the same element. A proper subset, A has elements of B or more. So I'll give you another example. Do we have any foreigners in the class? I forgot. Please, can you tell me whether we have any foreigners in the class? Class rep, are you around? Yes, please, class rep.
Yes, we do
Uh,
have one.
Okay, thanks. Right. So A here in this case, A has some element, same element of B or more, right? So if it has 1, 3, 4 same element in there or more, then it is a superset. If it's a proper set, A can have more elements like 5 and 6 here, right? So then it is a proper superset, right? You can see in this example right away here, 1, 2, 3, 4, A has more elements than than B. Okay, if it does not have any element, all the elements from B, then it is not a superset. Is that okay, my friend? Did you understand it?
Thanks,
Whoever
Eddie.
else- Yes.
I think I need practice to understand it a bit more.
Yes, definitely. Set notations. So what do we have? Complement. So what is a complement? Elements not in A. A minus B. What's the difference? It is the difference. Have a look here. So this is A. This is B. So complement is everything that is not in the set. So A minus B, you have to be very careful about that. A minus B and B minus A will not be equal. Okay, you have to be very careful about that. So 1, 2, 3, 4 minus 3, 4 would be 1, 2. Okay, if it were to be the inverse, it would be different. Okay, so 3 being an element, so this is read as A being an element of the set A. Remember, A is an element of the set. It forms part of the set, and capital letter A, the capital letter simply defines the set. Okay, you have to make the clear distinction between those two things. Okay, it's not the same thing. Whenever you're using capital letter, it simply denotes the set, and then small letters simply denotes the element of the set. Okay, so 3 being an element of the set 1, 2, 3, 4. Just give me a second. Okay, so sorry about the call. This denotes an empty set. So this being not an element of A, this denotes an empty set. So empty set can also be denoted as two brackets with nothing in between. This denotes a universal set. This simply says that objects that belong to A or B, but not either but not to their intersection. What does that mean? Have a look here. So you will see that the intersection between A and B is 3, right? So if you do this, it will say whatever is not in not intersecting between those two would be 1, 2, 9, 14. Okay, a power set is so the power set of 1, 2, for example. So if we have a set A is equal to 1, 2, right? So the power set of A would be this. Okay, so you'll have an empty set, you'll have 1, you'll have 2, and then you have 1, 2. What is a power set? All the possibilities, all the possible subset of a set. Okay, so equality, A is equal to B, so the sets are equal, right? It's some kind of just like this one. It can be a superset as well. Okay, Cartesian, not all cases though, we'll see those situations where it's not the case. Cartesian product, set of ordered pairs from A and B. Okay, so if A is 1, A is equal to 1, 2, and B is equal to 3, 4, right? So the Cartesian product would be 1 with 3 and 1 with 4. So it's going to be 1, 3, 1, 4, and then 2, 3, and then 2, 4. So all the possible products in there. And cardinality would be simply the number of elements in a set. So the cardinality of B, for example, of the set B, where B is 3, 4, the cardinality would be 2. Okay, so far so good. Everyone is able to cope with whatever we're saying? Can I have a
Sir?
feedback? Yes,
Yeah.
Sure.
Ashley.
Ashley. Yes, Ashley. Yes.
For the complement, I haven't really understand element, nothing.
For the first one,
This-
A
yes.
complement, right? It is very simple. Let's say you have a set. Let me just delete that. It will be much easier. Whenever you don't understand, you can use Venn diagram, okay? So if you have a set A and a set B, for example, and then this is the universal set, right? You understand this, my friend, Ashley? Ashley, are you there?
Yes.
So if you wanna say A complement, it would be everything which is outside A. Is that okay? So A complement is if you say D, suppose that D here in this particular example, D should have been 3. Sorry about that. 5, 3, 4, 5, right? If we say D complement, it's going to be 1, 2, 6, 7. Is that okay, Ashley?
Yes, sir.
Good. It's good you clarify before we move on to the next part, okay? Set notation. This stands for such that. This also stands for such that. This is extremely important for predicates and so on and so forth. This stands for all. If we say this X, this stands for all X's, right? Depending on, remember that we're using small letter here. This stands for there exists. We can say there exists or for some. So what we're saying that for some values of X, right, something will happen, some values, okay? So very important that you understand this, the difference between these two. In the exam, we see students writing for all like this, right? So it's going to be wrong. If you're going to write for some or there exists like this, it's going to be wrong again. Please remember for all is like this, and for some or there exists is going to be an inverted E. This is therefore, these are natural numbers, these are integers, these are rational numbers, these are real numbers, imaginary numbers, complex numbers. The ones that we tend to use a lot in this module are natural numbers, integers, rational numbers, real numbers, and complex numbers. Imaginary numbers are very we don't want to push it that hard for you to use imaginary numbers, but it's good to know what are imaginary numbers. Okay, there is a YouTube video by a guy known as from a channel known as Veritasium. Go and check it out. I think they just released a video this week itself on imaginary numbers, where it all came from. Why do you have imaginary numbers? They figure out, as far as mathematics is concerned, go and try to figure out the the background of mathematics, the guy was talking about quadratic equations, cubic equations, and all these type of equations. Why did they come up with, for example, why do you need to understand the equation for this parabola, for example? Why do you need to understand the equation of this? Why do you need to know the equation for a power curve? The reason is pretty simple. He explains that very nicely. He explained that, you know, the world is made up with a lot of parabola. For example, that could be a bridge, the layout, the elements that support a bridge. So that could be the bridge here. And that parabola could be the main structure that supports the bridge. So how would you how would you calculate the force that is exerted, that will be required, or that will be exerted on the bridge? So you definitely need to be able to model this. Now, this is one element only, but we can go beyond that. If you look at, for example, in a software, you're developing a software, let's say for an ERP, for example, and ERP stands for Enterprise Resource Planning. This is one of the most common systems that most of you will be developing in the in an IT company. A lot of time you will be given a profit curve that you will have to, so you're computing all the revenues and the expenditures, expenses, and then you need to come up with a profit curve, and then you need to, your system should be able to optimize, try to increase the profit, try to do some reverse engineering. So if you set a profit, so this is your profit, your current system is taking that much profit, and you need to, your system should use some BI or some other technology, some intelligence to raise the profit. This is the targeted profit. Obviously, this has to do with mathematics, okay? So that's why it's so important. I'm drifting a little bit off topic for today's session, but it's so important to understand the mathematics behind that. It will be pointless. As I said, the industry, if you look at the industry right now, companies like, I don't know if you know about that. Accenture, for example, is doing a conversion course. I think I don't know if I mentioned that earlier on, a master's conversion course where they're taking engineers, people with good mathematical background to convert them into IT people, programmers. The reason is pretty simple. Those people with good mathematical background can solve problems even better. So bear that in mind all the time, okay? So relations between sets, okay? It's pretty simple to understand this. Suppose A and B are sets, then A is called a subset. A is called a subset of B if and only if every element of A is an element of B, okay? You can see here, every element of A is an element of B. So that could translate to this. If you don't understand, you can use sets, you can use Venn diagram, whichever way, you can use both. If 2A is equal to 2, 3, and here, I don't have enough space, B is equal to 1, 2, 3, 4. So A is a subset of B, pretty simple. So A is a subset of B. See, for all x's, if x is an element of A, for all x's, what is simply saying for all the elements in the set, right? If x is an element of A, of the set A, then x is an element of B. A is not a subset of B when they are disjoint. This is known as disjoint. That is, there exists some values of x such that x is an element of A. X is found. You have an element in A, let's say, but x is not an element in B. So that could translate to A is equal to 1, 2, 3, and B is equal to 3, 4, 5. These are the x's that you're going to have in there, right? So for some, there exists some values of x, okay? So A may not be a subset of B. Another situation, A may not be a subset of B if you have an intersection as well, okay? So that could be a situation as well. Okay, let's move on. So A and B, A equals to B if every element of A is in B and every element of B is in A. This is something this is called symbolic. This is extremely important, equality. So how do we represent this? Whenever you want to prove equality, remember that all the time, because we're going to prove that a lot of times in many, you have many questions in the exam and in the test that ask you to prove that this is an equality. So this element, this set A is equal to the set B. So how do you prove that? You'll have to prove that A is a subset of B and B is a subset of A, right? So you'll need to prove that A is a subset of B and B is a subset of A. If you've been able to prove it both ways, then there is equality. An example, let A M being a set of integers such that M is equal to 2k plus, this is what is known as a complex number, what we've seen earlier on. Okay, for integer, this will generate complex number, but they will be still integers. For some integer k, B is the set of all odd numbers, then A is equal to B, right? So let's try, I mean, later on we'll try to do that. We'll have the proof for this one. So what he's saying is that in this set, when k is equal to 1 for some integer, right? When k is equal to 1, for example, M would be equal to 5. And when k is equal to 2, this will be equal to 7. When k is equal to 3, this will be equal to 2 times 3, 6, 9, right? So you'll see that if you look at integer, if we looking at the set of odd numbers, of all odd numbers, it will be the same thing, right? Mind you one thing, so I can use ... here. This can also be represented if we use negative numbers, right? We can redo the set of odd numbers. We can also have 1. So, for example, we can also have 1. We can also have 3 for this one. We can also have 5 for this one, and it goes on like this. So if you want to prove equality, you need to prove that A is a subset of B and B is a subset of A, and this is easily doable. Okay, so operation on sets, pretty simple. Let A and B be subsets of a set U, of a set of a universal set. Okay, union of A and B is simply X being an element of the universal set, X is an element of A, or, very important, X is an element of B, right? Intersection, so A being an intersection of A, so A being an element of the universe, X being an element of the universal set, X is an element of A, and X is an element of B. So this will be an intersection. Intersection simply says this. So the element should be here, right? So a element of the set, okay? So the difference B minus A, so X is an element of B, but X is not an element of A. So if this is A and this is B, so X should be found somewhere in here, but not in A, okay? X is a complement, A complement. So A complement would be everything which is outside the shaded region here. Everything outside the shaded region is there. So you have a little example. So A is between 3 and 5. B is between real numbers between 4 and 9. So since they are real numbers, we are using a set builder notation to describe them. A union B would be everything between 3 and 9. So that's the union. intersection will be anything between 4 and 5. B minus A, this is the thing that I wanted to make you understand earlier on. B minus A is 5, between 5 and 9, including 5. And A minus B, you can just list them if you're having difficulty here. So here it will start with anything between 3 point something till 4.9 something. Okay, so here it will be anything between, for B, 4 point something, and anything that goes between till 8.9 something. Okay, so the B minus A, if you have to remove these elements there, so it would be anything between 5 point something till 9. Okay, 8.9 something. A minus B is 3, between 3 and 4. Okay, A complement is anything between, which is less than 3 and greater than 5. So less than 3 and greater than 5, right? Remember, you have a universal set. That's why we're catering for less than 3, right? The universal set being the set of real numbers, right? And anything which is greater than 5 is A complement. B complement is anything which is less than 4 and greater than 9. Okay, pretty simple to understand. It's not difficult. You have a little exercise here, so give it a shot, and then we'll correct it in a few minutes. Please go ahead.
So I cannot see the screen.
Yeah, just give me a second, please. If you have this, make sure you have also the slide in front of you. It's very important that, just give me a second, just sorting out my screen issue. If you can have the slide in front of you, it would be much easier. I'll put it back in a few minutes. So I hope you can see the full presentation and my me writing up here. Can you just let me know?
Yes.
Okay.
Yes.
So what is A union B? Anyone can tell me? Any volunteer, please? A union B?
Sir,
Yes. Yes, who's speaking?
it's Ashley.
Yes, Ashley.
A union B is A, C, D, E, F, G.
Yes, I agree with you, my friend. I'm sorry about the slide. Start again. A Just give me a second. Having issues with my slides. Yeah, I agree. I'm just gonna say it again. The answer for this one, for some reason, the slide is going bonkers. So A union B would be A, C, D, E, F, G. Totally agree with you. So if it's gonna write, I don't know what's going wrong with my slides today. Just give me a second, trying to sort this. The section B would be? Yes.
The answer would be ENG.
That's very correct. I agree with you. ENG, very simple. B minus A.
DNF.
Say it again.
DNF.
DNF, pretty simple. A complement. B, D, F. Is that okay?
Yes.
Yes,
Okay.
sir.
Yes. Who's speaking?
English.
Yes. Question?
So the third part,
Yes.
the answer should be A, C, D, F.
Nope. B minus A. So you need to take common element from E and G. So I'm having issues with my, just give me a second. I'll try to sort it out. I don't know why I'm having this issue, but it's getting a little bit frustrating now to use the PowerPoint. So let me just try to get. Just give me a second, trying to sort out the problem. Right, let me just share this. Right, can you see my screen?
Yes.
Okay.
Yes.
So let me just explain this. So you have A is ACG. Right. Okay, so what we want, the question says B minus A, right? So let's do it together. B minus A would be, so B is, you need to remove A from it. So what do you have in common in, so this is A and this is B. So you need to remove what you have. The difference would be what you have in common between them. It's not A minus B, it's B minus A. So you need to take the common thing from this one and, sorry. You need to take the common element from this one and remove it from this one. So the common element is this. So that would be, what are you left with is DF. If you were asked to be to calculate A minus B, then it would have been different, right? It would have been AC. Is that clear, my friend?
Yes.
Good. Okay, let's move on. I'll give you a 2 to 3 minutes break because I know you must be tired by now. and then we'll move on 2 to 3 minutes. It's not going to be long. We'll move on to the next elements. Okay. Small little break, and then we're going to be back.
Yes, sir.
Okay, let's move on. Okay, I can see a few students still using your nickname or your you not have your name in full on the Zoom session. Bear in mind, whenever we're going to take your attendance, well, most likely you will not be present because we don't have your name in full, so that's problematic. So bear that in mind. So if you're going to, as I said last time, if you're going to use short names, nicknames, whenever we're taking your attendance, you will not be present in the class, though you were present. Okay, right. So let's move on. Okay, sets of real numbers. These are some example. Again, some further notations. So some additional example and notation. Given real numbers A and B with A less than or equal to B. So the set A and B, X are real numbers between A and B. If we have a set with the square bracket on this one, please remember this, okay? Square bracket on this one, I hope you can see that, the square bracket on this one. What does that mean? A is less than or equal, X is less than or equal to, so A from A till less than or equal to B, okay? So that means it will include B in there. If the square bracket is on this side, if the square bracket is on this side, the less or equal to will be on this side. So what does that mean? It will include, what does that mean? It simply says that it will include A in there. So if the square bracket is on both sides, if the square bracket, I'm sorry, I don't know what's the issue with my tablet today. My graphic tablet is just going bonkers. or is just looking for a replacement. So the equal to would be on both sides here. So bear in mind, this notation is very important. Having a square bracket is very, very important. So please please take that into consideration, okay? So the simple, infinite, negative, infinity are used to indicate intervals that are unbounded, either on the right or on the left. So you'll see that these are infinite. X is greater than or equal to a. So X is greater. So you'll see that you have the limitation here of the boundary, a up till infinity, X, you'll see the boundaries. So definitely you'll have the equality sign here, okay? So to prove A is a subset of X, pick an element of X, assume that X is in X, show that X is also in Y. This is called the element argument, right? So if you want to prove that X is a subset of Y, pick an element X, any element of, just rewrite this to avoid confusion. Pick an element, any element of X, of the set X, and show that X is also an element of Y. Okay, so it's pretty simple to understand this. Okay, if you have any issues, please let me know. Now, this is where we start to get into the, so we've been dealing with notations, trying to understand notations and so on. Now we get into the gist of the subject of what we will be dealing with in the future. Okay, I know that I'm taking numbers as example in the lecture, but you'll see that as we move on to the practice, it will be a little bit more straightforward because the examples will get more in terms of a varied number of examples or problems or scenarios. Okay, so theorem theorem 1 says some subset relations. A intersection B is a subset of A. A is a subset of A union B. It's pretty straightforward. What we're saying, A intersection B, so if that is A, if you can't understand it, simply draw it, okay? A intersection B, so that's A intersection B, is a subset of A, so it is found in A. A is a subset of A, is a subset of A union B, the entire of both sets. A is a subset, this is interesting. A is a subset of, if A is a subset of B, and B is a subset of C, then A is a subset of A. So if A is a subset of B, A is a subset, so this is A, and this is B. So if A is a subset of B, and B is a subset of C, then definitely A is a subset of C. Pretty simple to understand this. To prove that A is a subset of B, use the element argument. So let, what is element argument? Let X be an element of A, and then you need to try to prove that X is also an element of B, right? How simple is that? Theory number 2 is the distributive law. Remember the name in there because there are so many questions, roughly 2 to 3 questions, I mean sub-questions will be using these laws, okay, in the test and in the exam. For many sets A, B, and C, for any sets A, B, and C, A union B intersection C is equal to A union B intersection A union C. What is the proof behind that? Since we have equality, right? Since we have equality, remember what we said. Whenever we have equality, we want to prove, how do we prove equality? A is a subset of B and B is a subset of A. We need to prove those two things. This is what is being done here. So we're proving that the left-hand side is equal to the right-hand side. Come on. Right-hand side, and then we'll prove that the right-hand side is equal to the left-hand side. So how do we do that? Remember we said if we want to prove something is a subset of something else, we need to use this thing, element argument, right? So we can say, for example, if we want to prove the equality, we'll say let X is being an element of A, for example, right? And then we'll need to prove that X is also an element of B. So therefore, we can prove that A is a subset of B. Then we'll prove that let X is for the second, so this is for the left-hand side. And so this is the left-hand side, and this is the right-hand side, right? So let X be an element of B. So therefore, X would be an element of A. So if we are able to prove that, we'll prove the right-hand side. So if that works out, both are subsets of each other, then there is equality. But in that particular case, since it is a very simple thing, we don't really apply that. But for these type of problems, the application of the element argument is very important. So suppose, let's see, let X, you can write suppose or let X be an element of A union B. So this is the left-hand side. You can see that. So we want to show that X is an element of A. We want to prove the right-hand side here, right? So to do that, it's pretty simple. X is an element of A union B intersection C. What does that mean? X is an element of A. So X is found in either A, the element is found in A, or the element is found in B intersection C. So it's either here or here. Let X equal B. If so we choose, this is number 1 and this is number 2. So let me just call it A. So that's A and that's B, right? So for A, right, let X be an element of A, right, of the set A. Then if X is an element of A, then we can say that X is also an element of A union B. If it's found, the element is found in A, if it's found in A, somewhere in A, so we can agree that if it's found in A, it's going to also be found in A union B. And X, if it's found in A, we know that it is in A, and A is also connected, for example, to C, right? Just giving an example here. I'm not drawing the exact diagram. So if it's found in A, so X will also be an element in A union C. Okay, so since it is found in A union C, which says that X is an element of A union B, and it's an element of A union C. So this is the end here. So that would be the intersection. So what have we done? Have we proven this? Yes, we have proven this, right? The right-hand side, okay? So vice versa, if X is an element of B intersection C, let X be an element of B and X be an element of C. If X is an element of B, then X is an element of A union B. If it's found in B, it's going to be found in A union B. If it's an element of, so since it is an intersection, what does that mean? X is an element of B and C intersection. So X is found here, right? So it's found in both B and C. So if it's found in both B and C, then X will be an element of A union B. X will be an element of A union C. So we have proven this as well. So this shows thus 2 and 1 is true. So 2 is true. Then we have shown that 1 is true and second is true. So this is how you prove equality. Obviously, you will try some exercise to understand it. Did you understand it, guys?
A little bit.
What's the confusion? Who is speaking? What's the confusion?
We need to.
Who is speaking?
Timlesh.
Say it again.
Timlesh.
Timlesh?
Yes, Kimlesh.
Kimlesh, yes. What's the issue?
We need to work some exercises so that we can
No,
better
what
understand it.
from this example, what you didn't understand?
No, it's like too many information in it takes time to understand
Okay,
this.
okay. Definitely you can understand it better whenever you have the exercises, but I'm just explaining the concept here. So if you've understood that the distributive law, we're trying to prove the distributive law that this is this element. So let me just use a different color here. That this element we're doing two things here. Number one is the distributive law. The distributive law says if A union B intersection C, then A would be then A union B intersection A union C. That's what is known as the distributive law, right? So that's number one thing that you need to understand. But this explanation goes a little bit further to explain to you why this is true. Why this distributive law is true. It is true because the fact that we've said that this is an equality, so A union B, this is, I say it again, this is the distributive law. I'll just call it DL here. This is the distributive law. Anything that is A, if you have a set A union B, B intersection C, it will always equal to A union B intersection A union C. That's the distributive law. Later on, I'll show you other laws like the commutative law, associative law, and distributive laws. This is what we've just done, okay? But to give you an insight of how you can prove that, how this, the law does not have to be learned by heart. It can be proven. If you want to prove this, since we are dealing with equality and what you've learned earlier, right? To prove this, you need to have to show that the right-hand side, the left-hand side is a subset of the right-hand side, right? And the right-hand side is a subset of the left-hand side, right? And to do that, so the left-hand side is a subset, so vice versa. To do that, it's pretty simple. So you take the left-hand side, you say X is an element of the left-hand side, right? So if X is an element of the left-hand side, you should be able to say that, you should get to the point to say that X is also an element of the right-hand side. If you're able to show that, then this will be satisfied. And then you do the inverse. You say, let X be an element of the right-hand side. Then through that, you try to prove that X is an element of the left-hand side. If you're able to prove that, then you're going to prove this one. If you're able to prove both, then this equality stands. Is that clear, my friend? I forgot your name.
Yes.
Okay, just to put it into simple. If you don't understand, please, it's not a, don't wait for the last minute. Don't only wait for exercises. If you didn't get the gist of it, maybe I'm going too fast. Maybe sometimes I take it for granted. It happens because there are so many elements to explain. I take it for granted that you've understood it. So you need to tell me that you didn't understand and I'll clear it out, okay? So coming back to the law, we've seen this is how it can be proven. We'll have a whole chapter on proof where you'll have to deal with these kind of things. Whenever you have equality, you need to prove that the left-hand side is a subset of the right-hand side. The right-hand side is a subset of the left-hand side. But coming back to the laws, these are the laws. The first law is known as, there are many other laws, but the basic one, the commutative laws. A intersection B is equal to B intersection A. So if you have two sets, A and B, and you're talking about the intersection, so A intersection B is the same as B intersection A. Again, if you wanted to prove this, you have to prove the right-hand side, the left-hand side, sorry. Left-hand side is a subset of the right-hand side, and the right-hand side is a subset of the left-hand side, right? So the same thing. If you have a union, A union B is the same as B union A. It doesn't make any difference. It's very it's pure simple logic to understand that. The associative law, this is an interesting one. The associative law says A intersection B, if A intersection B intersection C, it will equal to A intersection B, B intersection C. Okay, you can draw this, right? It's very simple to understand it. You can put it this way. So if this is A and B, and this is the intersection of A, so this intersection, we can add a C here. So this intersection, this is what we're talking about here, this area here, right? So whether you're talking about A intersection, whichever intersection you're saying, it will just be the same thing, okay? So it's equally the same thing. The inverse for union, it will just be the same thing, okay? So whichever way you inverse it. So a distributive law is what we've seen here. A union B, when it's not the same, right? When it's not the same, so you have different union and intersection. So the intersection here, so if this is a union, this will become an intersection. If this is an intersection, this will become a union. This is how you remember it. The rest will be union. Okay, so whatever is before the bracket, it will be inversed, and then the rest will be intersection for this one if this one is union, and then union if this one is intersection. Okay, again, we're not going to go into you can draw it to understand it. It's not difficult. You can draw it to understand it, but you can put values for this one to understand it. Just put some values. A is equal to some element, B is equal to some element, and C. This is how usually you try to understand this. If you're going to draw Venn diagrams, it's going to be a lot complex, difficult to draw them. So try to figure out some elements, A union B intersection C. And when you try to do the union of these A and B and the union of A and C, and when you do the intersection, the value that you're going to have here and the value that the elements that you're going to have here should be the same. Okay, so this you can try it as a homework. It's very easy to understand this. Okay, so double complement. So you see, you know that A complement is everything which is outside A, but if you say everything which is outside A and the complement of that, it simply brings you back to A. Let me just give you an example. If you have A, this is the set A, and this is the universal set, right? So everything which is outside A complement is outside A. Now you see the complement of everything which is outside A, then it's going to come back to A again. So if a set you have A is equal to 1, 2, 3, and the universal set you have 1, 2, 3. That's why I say sometimes you take the elements, it's much easier. A complement would be 4, 5. Now, the complement of A complement would be everything which is outside the A complement, 4, 5. So you will end up with 1, 2, 3. So you get back to A. So this is what is being said here. Everything can be proven. You don't have to learn by heart. You just need to simply understand it. The way if you remember, if you ask me how I remember it, it's pretty simple. I just use elements to remember them. So I try to get a set and try to explain. It takes a little bit time, but just a few seconds more, but it works out. The De Morgan's law is an interesting law. If you have complement, De Morgan does not apply for this one, but you'll see other De Morgan's law. A intersection B complement would be A complement union B complement. So when you remove the bracket, the intersection becomes the union here. When you remove the bracket for this one, the union becomes the intersection, right? Again, try an example. So we already have, just get A and B, 1, 2, 3. So let's put it very simple, 3, 4, 5. So A intersection B would be 3. Now the complement of A intersection B, A intersection, this thing. I don't know why my marker is doing that. There you start again. So there you go. So A intersection B complement would be 1, 2, 5, right? So you expect that this will yield the same thing as this one. So this is known as the De Morgan's law, okay? So you can try it out. What I will ask you, each and every of these laws, you have to try it out. If you don't try it out, right? You don't try it out at home after the lecture, don't take too much time, wait for a day or 2 days to try it out. If you don't try it out, trust me, the next 4 chapters that you're gonna do, we will be doing, will have, we'll do with this. Okay, so you need to try it out to understand what we are explaining. We're trying to explain here. The absorption law says A union B, A intersection B is equal to A. Right? If you say, let's put it this way. Let's take this example for instance. Let me just erase that. This is known as the absorption law. So A intersection B would be 3. A union intersection. So if you do A union A intersection B, it would be this. You'll have to do this and this. So it comes back to 1, 2, 3. So this is equal to A. If you do the inverse, A intersection A union B, it will come back to A as well. This is known as the absorption law. So far so good, guys. So far so good. Tu comprends?
Yes.
Yes, sir.
Yes.
Some feedback on the chat as well, all of you. Please reply back so that I know whether you are able to understand or not. Okay, let's proceed then. So we have, in case you didn't understand, feel free. It's not a problem, okay? Feel free to voice out. Okay, let's move on. Share. So can you still see my screen?
Yes.
Okay, so showing that an alleged set property is false. So one is a set false, right? Statement for all sets A, B, and C. A minus B minus C is equal to A minus B minus C. So how the following counterexample shows that the statement is false. So how are you going to prove that? Again, you use a an example. So A is equal to 1, 2, 3, 4. B is equal to 3, 4, 5, 6. C is equal to 3. You use that example. B minus C is equal to 4, 5, 6. A minus B minus C is 1, 2, 3. On the other hand, A minus B. So you want to, remember, this is the left-hand side and this is the right-hand side. So when you use a counterexample, when you use an example, you just need to prove that the value of this one is not equal to the value of this one. So A minus B is 1, 2, and A minus B minus C is 1, 2. So you can see the difference between them. So it is not equal. So no equality. Okay. Empty set, a unique set with no elements is called empty set and denoted by this symbol. The set properties that involves this. For all sets, this is always a subset of A. A union an empty set is A. A intersection null is null. A intersection the complementary of A is null as well. So what you're saying is that this is A and this is B. So whatever is outside A is this. So it's B, right? So what you're saying, A intersection this, there is nothing in common, that would be null, okay? Disjoint sets, so what sets are disjoint, so this is A and this is B, or you can write it this way, this is 1, 2, 3, and B would be 4, 5, 6. So they are disjoint. They are called mutually disjoint. So A intersection B, for example, would be null. A is equal to 1, 2, B is equal to 3, 4 are disjoint. The sets are of even numbers. So if you have a set of even number and a set of odd numbers, they are disjoint. So you have another example, A minus B, B minus A, and A intersection B are mutually disjoint. If you try this out, you'll see that they are mutually disjoint. Some example. Now, why are we studying all this? It's very important because remember what I said earlier on, later on, you'll have to understand relationship between sets. So one set will not interact with another set, for example, okay? We'll have no, they are mutually disjoint. There is no intersection between those two. There are no commonalities between those two. If there are commonalities, that adds complexity to that, so that you can understand the complexity within sets. Partitions, a collection of non-empty sets, very important. These are partitions, non-empty set. So if in a set you have A1, A2, A3 is the partition of set A, if and only if the union of all these subsets will be A, and A1, A2, A3 are mutually disjoint. There is nothing in common between those sets, right? They are mutually disjoint. So A1, what I'm trying to say here, A1 intersection A2 intersection A3 intersection A4, right, is null. Okay, so none of them have intersections. Okay, so they are mutually disjoint. For example, if you have a set of positive integer, a set of negative integer, and the set of 0 is a partition of Z of integers, but remember, they are not mutually disjoint. Okay, so some other examples here, you can try this out, try to understand this. So you have complex numbers here, n is equal to 3k, n is equal to 3k plus 1, n is equal to 3k plus 2. They all form part of integers, right? So n are integers, sorry, this integer. They are all sets of integers, of the partition of integers, but they don't have anything, they don't have any intersection. So power sets, I'm just going to go a little bit faster because it's much easier to understand now. Power set is denoted by, so if you have a set A, and A has, for example, 1, 2, I think I explained that earlier on. So the power set of A would be 0, null, okay, or empty set, and then 1. Remember to use those braces, 2, and then 1, 2, right? So if you have here, if you have a set, the set includes A and B, so you can see the different elements in there. The properties, if A is a subset of B, then the power set of A would be a power set of B. If A is a set, if a set A has n elements, then the power set would be 2 to the power of n elements. It's pretty simple. How many elements do we have in the set? We have 2 elements. So the power set of A, how many elements do we have? 2 to the power of 4. So you need to end up with 4 elements. So if you count this, 1, 2, 3, 4. If a set has 3 elements, so the power set of A here, the number of elements is 2 to the power of 3. That would be 8 elements. Okay, so pretty simple to understand that. Okay, now why do we use power sets in programming? This could be something very interesting. If we have a set and we want to make combination, if we had we're defining a variable and we need to make combinations of these variables to know all the possible elements of combinations in there. For example, if I ask you to write a little program to schedule, to look at the possibilities of scheduling meetings between 3 persons. Let's say those 3 persons are, let me call the variable person. So you have a first person known Paul, and then you have a second person known John, and you have a third person known as Smith, right? So these are the 3 persons that we have. So if I do a power set of person, it will return me all the possibilities of a meeting in there. So I can have a meeting with no one. I can have a meeting with Paul on a meeting just with Paul only, a meeting with John only, a meeting with Smith only. I can have a meeting with Paul and John, and I can have a meeting with Paul and Smith. I can have, and it goes on like this. So this is known as a power set. Nowadays in programming, you have functions that are already defined in libraries that can help you to do power sets. But unfortunately, a lot of computer scientists, a lot of software engineers don't understand the concept of power sets. They simply just use it. It's not even named as power sets in programming, but they don't understand it, okay? So an example here, so if the set has element X and Y, so these are the possibilities, right? This is very important, okay? If you have a set which is null, there is nothing there, so the power set of that will be null, all right? So if you have a set, very important, huh? The set is null. If you have nothing, right? Sorry, let me just voice it out. If you have a set with nothing, it will be, the power set will be null. If you have a set that contains an element of null, then you will have null and the set of null, okay? This is very important to understand that. The braces makes a huge difference. So if A is empty, the power set of A would be empty, right? If A is a set containing an empty element, right? So the power set of A now would be empty set, null, and the empty set. Okay, very important. So size of power set, so 2 to the power of n, very important. Already explained that. Remember that all these will not be given in the exam. And it will not ask you in the exam to calculate the number of elements in there. When do you use that? Whenever you are asked to calculate the power set of a particular set, simply just do 2 to the power of n to make sure that you've listed all the elements in the power set. This is the only way for you to verify it, okay? Cardinality, I presume we are almost there, and then there will be product. Cardinality is of a set, the cardinality of a set A is simply the number of elements in the set. So it is represented most likely by these two columns there. So the cardinality of a set A, if A is equal to 2, 4, 6, that is, this is A. So the cardinality of A would be the number of elements that you have in there, right? In programming, if you have an array, I don't know if you know what I'm talking about, or if you have a list, right? Most of the time you use a concept, a loop to count the number of elements, the number, to count the number, the size of the array, not to count, but to find the size of the array. What you're actually doing is the cardinality of the set. It's exactly the same concept, but the only problem with us programmers, we tend to forget about the mathematics, okay? Now, very important, if the cardinality of A union B plus the cardinality of A intersection B would be the same as the cardinality of A plus the cardinality of B. Okay, try it out. Okay, if you have a set A, which is equal to 1, 2, and a set B is equal to 2, 3, 4, A union B would be 1, 2, 3, 4. So the cardinality of that is 4. 4. A, I hope you understand what I'm doing here. A intersection B is 2. So the cardinality of this one is 5, right? The cardinality of A is 2, and the cardinality of B is 3. So that's 5 as well. So they are equal. If A and B are disjoint, then the cardinality, so A, let me just change it to a different situation now. So if A and B are disjoint, so let me just change that. So disjoint, so A union B would be 1, 2, 3, 4. So the cardinality is 4, and A is 2, B is 2. So here the cardinality is 4. So they are equal. Okay. Cartesian product is pretty simple. It's very important to figure out different combinations in programming. Whenever you have arrays where you want to come up with matrices, this is a very common problem. If you have a graph, let's say you're on Google Map, you want to know this is your current location, you want to move around, for example. So these are all coordinates, like for example, this is 1, 3, whatever it could be GPS coordinates, it could be any type of coordinate that you're using. Obviously, this is point A, this is point B, this is point C, point D, E, F, G. You want to know the distances between them, so you can use multi-dimensional arrays. So that could be A, B, C, D, A, B, C, D, and it goes on like this, okay? And you can figure out the distances between them, right? And you can put those distances here. Between A and A, the distance is 0, between A and B, and so on and so forth. And you can use Cartesian products, right? To find quite a number of things, okay? So what is that is simply if you have a set S and a set T, A, B, C, the Cartesian product would be 1A, 1B, and then 1C, and then 2A, 2B, and then 2C, okay? The Cartesian product for T and S, right? T times S will be different. So you will start with T now. The arrow will have a different, so A1, A2, then we go B1, B2, and then you go C1, C2, right? So cardinality ST, S product T, and T product S is not the same, okay? Very important to understand that. So I hope you've understood the main element. Unfortunately, we didn't have time to take some exercise, but any questions so far, guys? Please turn on your mic if you have any questions. Any questions?
No.
Okay, since we still have 5 minutes, maybe I can throw in a small little question that can help you out understand a little bit more what I'm trying to explain here. Let me see if I can put a question there. Over and above the homeworks that you have to do.
Sir, the question
Yes?
set in Google Classroom is empty.
Yeah. Let me just sort this one out before I leave. Let me just add it there. Did you all understand the concepts? Did I make it clear enough? Maybe you can, by the time I add it there, we are left only with 4 minutes. By the time I add it there on Google Classroom, please drop in your comment in the chat so that I get to know whether you didn't understand it or you didn't understand. Is it clear? Obviously the exercise will make it clearer, but as far as possible, did you understand it? This is what I want to know. Okay, so the question are not there. So let's figure out about the question.
So,
Yes.
so what is a Poiru speaking? What is the
What is
difference?
what?
What is the difference between subset and superset?
Okay, I'll come to that in a few minutes. Let me just. Just give me a second. I'm just sorting out the question. Okay, just give me a second. Let me just answer your question. I'll post it in just after the lecture is over. I'll post the question. Okay, your question is, Who's speaking? Who was speaking?
Jules Poirot.
Yes. What was your question? Say it again. What is the difference between a subset and a?
Superset.
Okay. Maybe I can show it to you in an example. Okay. The A, if you look at a subset, A is a subset of B. A has some elements or all elements of B, and a superset A has same elements of B. Now, I think to answer your question, let me just try to in the exercise. I think I have a question there that makes it a lot clearer for you to understand it. We're running out of time because I need to release this Zoom session because another colleague will use it. Allow me to throw it as a question to you, my friend. Are you there?
Yes, sir.
Allow me to throw it as a question to you. Try to answer the question, and then we'll take it in the tutorial. Is that okay?
Okay, sir. Thanks.
Right?
Yes.
Okay, guys, so drop in your comments. I'll have to release this Zoom session, unfortunately. We don't have enough time. So drop in your comments before you leave. We left just with a few minutes. So drop in your comments in the chat so that I know whether you have queries. I can attend your queries in the tutorial. So drop in your comments. Till then, take care. And for those of you who have just used your short name, unfortunately, we will not be able to take you on board in the attendance because I can see Aftab. I don't know who is Aftab, so he will remain as Aftab there. Okay. Take care. I'll see you in the tutorial on Wednesday, and the tutorial will be on this Wednesday. So try to stick to your grouping as per your PC's instruction and join the group. It's going to be a Google Meet session, right? You'll see a Google link in the classroom. So you'll join through the Google Meet session. Okay. Take care. Remember to join on the Google Meet, not on the Zoom session. Okay. For the tutorial, Google Meet. Take care, guys. I'll see you next week. Enjoy yourself. And most importantly, stay safe. Take care. Bye-bye.
Bye, sir.
Au revoir, monsieur.
Au revoir, monsieur.
Bye, sir.
monsieur.
Goodbye, sir.